Good morning. How are you guys? I am so excited to talk to you today as we do page 65 with section 1 review. So, first of all, please understand that sometimes my camera skills are not the best. Let's take a look at number 1. The main idea: differentiate among the three particles of an atom in terms of their location, their charge, and their mass. Well, let me get this in focus. First, we have a proton. It has a positive charge. It's located in the nucleus of the atom, and it's big enough to affect the atomic mass. Whoops. I'm trying, guys. Neutron. First, it has a neutral charge. There's absolutely no charge. It's also located in the nucleus, and it's also big enough to affect the atomic mass. In fact, if you add protons and neutrons, you get the mass number. And then we have electrons. And electrons are kind of funny. They're not located in the nucleus. They are in this big cloud outside of the atom. And we call where they exist, we call those energy levels. And it's outside the nucleus. Electrons have negative charges, and they are so tiny that we do not consider them when we're adding for atomic mass. We only consider the proton and the neutron. Okay, number 2. So, infer why the elements magnesium and calcium have similar properties. If you look in the back of your book, you will see, let me get this here, magnesium and calcium. So they're in the same vertical column. And it happens to be column number 2. These numbers along the top of the columns those numbers refer to which family or which group your elements are in. So magnesium and calcium happen to be in family or group 2. Bear with me, I'm trying not to make you car sick. So because they're in group 2, that means that they both have 2 electrons in their outermost energy level. When we draw them, we draw circles. And so with calcium and magnesium, actually every single element in column 2 has 2 electrons in the outermost energy level. We call those valence electrons. And the reason that makes a difference is because that means those 2, calcium and magnesium and beryllium and everything else in that column will bond the same way with other elements as the rest of them. So that's what that means. Number 3 asks you to illustrate how a neutral atom becomes an ion. Well, my explanations are going to be larger than probably what you guys wrote for these because I'm trying to give you some background as well. So let's take a look at what I drew. Let's see, what did I draw? I drew lithium and I drew fluorine. And these 2 things are going to bond together. When lithium bonds with fluorine, it actually loses that electron on its outer shell. Well, if you lose a negative, what charge do you come up with? If you're losing a negative, this will now be positive. That atom turns into an ion. And an ion just means it has a positive or negative charge. So if you look at this, lithium is going to lose 1 electron. If you lose a negative, your charge becomes positive because you're getting rid of an extra negative. So now, if you lost that, you have 3 protons and they all have a positive charge. And now you're only left with 2 negatives. that means you have an extra positive charge, which gives your whole atom a positive charge. Let's look at what happens to fluorine, because when it takes that electron from the lithium, it's adding a negative charge. So what do you think is going to happen to fluorine? Well, let's take a look. So fluorine is now going to gain a negative. When you gain a negative, your charge becomes negative, because now fluorine is going to have, let's see here, 10 electrons altogether, and it only has 9 positive protons. So we have more negatives now than we do positives. That's why it ends up with a negative charge. Number 4 asks us to compare and contrast these isotopes. Now they are giving us uranium-239, uranium-238, and this is like normal uranium, and uranium-235. First of all, I want you to understand these numbers that they are giving us, those numbers, they are telling us the mass. So this is uranium-238. Well, that's the normal mass of uranium. So that's not really an isotope. Let's take a look at this. So the answer would be these are all isotopes of the same element. They're all still uranium. They all still have 92 protons. You don't change the number of protons in an isotope. Otherwise, you changed it into a different element. But this, uranium always has 92 protons. So what do we do? How did this change? Why are they all different numbers? Excuse me. Well, isotopes simply have a different number of neutrons in the nucleus. And the more neutrons you have of the same version of that element, it means the heavier that element is. If we did the math, we would find out that uranium-239 has 147 neutrons. How did I do that math? If you look at your periodic table, you will see that uranium has 92 protons. It's number 92 on the periodic table. I know how many protons it has because I see that number. Well, uranium-238, that is the mass. 238 is the mass. So I'm going to take 238 and I'm going to subtract 92 in order to calculate the number of protons I have. So 238 minus 92 gives me what? Right here. This is going to give me 146 neutrons. And that's how I 146 neutrons. That's how I calculate those. And so I just did 239 minus 92, 238 minus 92, and 235 minus 92. You take your mass, which is here, subtract your protons, and then that'll give you the number of neutrons. And I know that that's more than this question asks for, but I want you to know how to do that, okay? Number 5, you had to illustrate a model of calcium. You also had to include the number and position of the protons, neutrons, and electrons. Well, of course you did, because that's how you do a model. Let's take a look and see, how do you know how to draw it? Well, the first thing you have to do is find calcium in your periodic table. And there it is. Calcium is number 20. Okay, so that we know that in our nucleus, we are going to have 20 protons, because that's what the atomic number means. It means we have 20 protons. Let's go back to the book. Calcium's mass, we're going to round it. So 40.078 rounds to 40, correct? So let's calculate our neutrons. 40 minus 20, well, that's an easy one. That equals 20. So now we have 20 neutrons. Perfect. And we also know, let me take you back here. We also know that if it has 20 protons, then it has to have 20 electrons. The only problem is now, how do you know how to draw the electrons in? Well, let me give you a little secret about the periodic table. Do you see these numbers that go down on the left-hand side of the periodic table? Sometimes they're on the right. But anyway, it's the numbers that go from top to bottom. And there are 7 of them, always on every periodic table. This actually tells me the number of energy levels or the number of circles I have to draw around the atom. So for my calcium model, I'm going to draw 1 circle to be the nucleus. Then I'm going to draw 4 more circles around it to fill in my electrons. So let's take a look. And there you have it. You see, this was my original circle. This was my nucleus. And outside of the nucleus, I have 1, 2, 3, 4 circles. Now, let me see each energy level or each circle can hold a different number of electrons. The first circle holds 2 electrons. That's easy. 1, 2. Well, I still have 18 electrons to go. So let's look at my note. The second and third energy levels or circles can hold 8 electrons. So 1, 2, and then you see I did 3, 4, 5, 6, 7, 8, 9, 10. Now, that's an actual rule in chemistry that states you fill in your electrons one at a time before you fill in pairs. So I want you to watch how I number these. And being Catholic, this makes it really easy because I always think Father, Son, Holy Spirit. So that's how I fill in my chemistry. So follow my numbers. We already did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then remember how it said you have to fill in single electrons before you do pairs? Okay, that means I have to separate these two, 19, 20. That's how you fill in electrons. Except for, of course, the very first energy level, they can only hold 2. So you can put them side by side and that's fine. But that is how you draw your electrons. I have lots of notes on this page for you, and I'm going to post a picture of it to help you remember how to do this. All right, number 6 asks us to interpret the representation of magnesium in the periodic table and explain why the atomic mass is not a whole number. That's a good question because if we only add protons and neutrons to get the mass, why in the world do we have decimals in the mass number? Well, it's not just for magnesium. So first of all, I wish the book wouldn't ask it like that. When you see decimals for the atomic mass of any element, not just magnesium, it's because scientists take the average mass of all the isotopes. Remember how an isotope has different masses of the same element because they have different numbers of neutrons? I guess elements have fat days too. Fat days, skinny days. But the different masses come from the different amounts of neutrons. And then they take all of the different masses and they average them together to get the atomic mass. So that's why you have a decimal. Okay, they're not counting like parts of atoms. They just do an average of all the different masses that you have that exist on Earth. Now, for the question that everybody's always so excited, the math in earth science question. All right. Sorry, guys, I'm getting bored too. As the radioactive isotope radium-226 decays, well, before I read any further, you know it's an isotope, and this 226 tells me the mass of the radium. But as this decays, it emits. Emits means that it loses 2 protons and 2 neutrons. How many protons and neutrons are now left in the nucleus? What is the atom's new atomic number, and what is the name of this element? So we're going to take radium-226. Well, the element has 86 protons. So if you take 226 and, wait a minute. If you take 226 and you subtract 86, you're not going to get 136. I think I made a mistake. Hold on. Okay, let's look at the original radium-226. Well, I looked up radium in the periodic table in the back of your book. So, radium, hold on. Come on. Radium has 88 protons. See, it's number 88. And 226 is the mass number. Now, in your problem, it said, as it decays, it emits. That means it loses 2 protons. Well, 88 minus 2 gives us our new number of protons, which is 86. Well, which element has 86 protons? And that would be radon. So radon is now the new element that it decays into. And it has 138 minus 2 because it said it also loses 2 neutrons. And so the new number of neutrons in the radon is going to be 136. So it's just a subtraction problem, but it's a little bit more complicated because you just had to know, hey, how do I find radium in the periodic table and then subtract to figure out the number of neutrons. All right? And if there are any questions about anything, please don't hesitate to email. I'm going to set up some practice videos that you can watch. I think I'm also going to put up the 7th grade video I made for their chemistry. I think it was a slideshow presentation, just to kind of give you some background knowledge in case you're thinking, oh, it's been 2 years since I've had this chemistry. All right? I hope you guys have a wonderful day. Stay safe, wash your hands, and I really miss seeing your faces, guys. Good night.